Today in this video lecture, you guys are going to be able to identify the subatomic particles in terms of their mass, location, and charge. You'll also be able to determine the number of protons, neutrons, and electrons that are present in a particular isotope of an element. You guys are going to differentiate between atomic number and atomic mass of an element, and of course, define and understand isotopes. Okay, so these are the goals from today's lecture. So we know that an atom is the smallest particle of an element that has all the chemical properties of that element. With that being said, though, there are also subatomic particles that make up the atom, identify its characteristics, and of course dictate its reactivity. So protons are in the nucleus. We know that Rutherford helped us figure that out. Neutrons are also in the nucleus. That is Chadwick's contribution to the atomic model. And electrons are in orbits outside of the nucleus, and those contributions come from Thomson and Bohr. So we're quite comfortable with the whole where does each of the subatomic particles belong, and that comes from our previous lectures. The charge of each of the subatomic particles are positive, neutral, and negative respectively, and we have discussed this also in the last lecture. But we do need to talk about masses and things of that sort. So let's go ahead and proceed. So right here we have a nice little summarizing chart, tells us our charge of each of our subatomic particles. Also, guys, these are the symbols that you want to use when you're shorthanding the subatomic particles. So a little lowercase e with a negative represents electron, a lowercase p with a plus sign, and a lowercase n with a not symbol. These are all ways that you can represent the specific subatomic particle without writing out their full name, if that's what you choose to do. The relative masses of our subatomic particles are as follows. Now, AMU are atomic mass units, and these are units that are actually referenced to another specific element on the periodic table, and we'll talk about that more later on. What you need to understand, or what you need to get into your head, is the relative size of these numbers. Okay, so neutrons, this is the mass of a neutron. It is bigger than the mass of a proton, not by much, but it is bigger. And then electrons are much, much smaller than either neutrons or protons. And that will come into play a little bit later in our lectures. So right now, neutrons, protons, then electrons. That is the order of decreasing mass. And then these are the symbols we want to use to indicate our subatomic particles when we're not writing the complete name out. So let's go ahead and let's expand a little bit on our understanding of the atom and its structure that we basically gleaned from last lesson. Okay, so the first thing we're going to look at is that the space occupied by electrons in an atom is way bigger than the space occupied by the nucleus. Okay, and if we go ahead and apply our concepts from last unit, which theorist helped us obtain or conclude this idea? And we would say Rutherford. And the reason why we would say Rutherford is because when he did his gold foil experiments, most of the alpha particles passed through the sheet of gold and subsequently the atoms in that sheet of gold. Okay, and so to give you a little bit of context to the relative size that we're discussing here between the space occupied by the nucleus and the space occupied by the electrons, if you look at the biggest stadium in the country, which is currently Michigan's football stadium, which holds like 107,000 people, something like that. If you take that stadium and on the 50-yard line you place a golf ball, that golf ball represents the size of the location of the nucleus, while the stands and remainder of the building represents the location that the electrons will occupy in an atom. So basically there is a humongous difference between the location occupied by the nucleus and the location occupied by the electrons. Okay, so the second concept that we've covered is that the nucleus holds both protons and neutrons. Rutherford and Chadwick contributed the research and studies that allowed us to understand the location of protons and neutrons. Okay, so I also want to point out here, guys, that our heaviest subatomic particles are held in the nucleus. Again, that'll be important here in a minute. All right, the third concept that we've discussed previously is that the nucleus is more dense than the location of the electrons. Okay, so remember, first of all, we have most of our subatomic particles, our protons and our neutrons, in the nucleus. We also just learned that the proton and neutron are heaviest, the heaviest subatomic particles by significant value, and they occupy the smallest quantity of space. So remember that golf ball with respect to the rest of the stadium. So since density is mass divided by volume, if we have our heaviest subatomic particles, we're going to have our heaviest mass, and it occupies the smallest volume area in the atom. Okay, and of course, the studies again of Rutherford and Chadwick are going to contribute to that. And the fourth concept that we've already kind of discussed but need to reiterate are that most of the volume of the atom is empty space. Once again, this is Rutherford and his studies and contributions. Why? Because most of those alpha particles pass through during the gold foil experiment. Okay, so these are the concepts that we've covered, and you should be very comfortable with explaining. Let's move on to our next concepts that we're adding. Okay, so we're going to go ahead and add two more concepts to our understanding of the atom. So first of all, atoms are uncharged. That's not to say that atoms can't become charged. We'll talk about that later, but for right now, atoms are uncharged. When we read them off the periodic table or talk about a specific element, we're talking about the neutral form unless stated otherwise. Okay, and in order to be uncharged, the charges on the subatomic particles have to be equal. So protons, which are positively charged, and electrons, which are negatively charged, will be equal in quantity inside an atom. The second concept that we're needing to know is that the atoms are not all going to have the same number of neutrons as protons. And we're going to talk about those with respect to isotopes here in a sec. Okay, so let's go ahead and let's discuss some identifying features that we can get off of periodic tables, as well as different notation formats that are provided in most chemistry textbooks. Okay, so the first thing we talk about is atomic number. Atomic number represents the number of protons that are in the nucleus, okay? And the atomic number can be found on the periodic table. This is the element symbol here. It represents what element you're talking about. But right above it, or sometimes to the left, or sometimes to the right, but above the element symbol, you are going to have a number. That number is the atomic number, which represents the number of protons in that specific element's nucleus. Now, another important concept that you need to glean from this is that the number that you have above the element symbol, or the atomic number, is always going to tell you the number of protons, and the number of protons always tell you the identity of the element. So every element has a specific number of protons. If you change the number of protons, you no longer have that element. Okay, now also there's another notation that we'll sometimes see, especially when we're doing different types of balancing for elements, but basically the atomic number in this format is written as the lower subscript on the left hand side of the element symbol. Okay, so make sure you know that. You'll be applying that later on in your homework. Okay, so mass number is the number of protons and neutrons that are inside a specific element's isotope, and we'll talk about isotopes here in a second. But mass number basically is the sum of the two. Now, mass number is an appropriate name. Why? Because we know that protons and neutrons are heaviest subatomic particles. So the mass number represents the number of those subatomic particles that are going to be contributing to mass. Now, the mass number is not the mass of the element. We will learn how to calculate that a little bit later. Okay, so another important concept that you need to take away from this is that the number only tells you the sum, the mass number only tells you the sum of the protons and the neutrons. It does not show up on the periodic table. So notice, mass number is not written anywhere in this example. Okay, so the mass number cannot be found on the periodic table. Additionally, when we're looking for mass number, when we're looking at specific equations, or we're looking at this type of format here, the mass number is going to be written on the left-hand side as a superscript. Okay, so now that we know what mass number and atomic number are and how to find them in the respective formats we've discussed, we're going to go ahead and talk about isotopes and their features. Okay, so now let's go ahead and discuss isotopes. Okay, so guys, isotopes are atoms of the same element, so they have the same number of protons, but with a different mass due to a unique set of neutrons. Okay, so isotopes are of a specific element are always going to have the same number of protons, but they have a variable number of neutrons. Okay, so basically, guys, this is just what occurs in nature. It's a naturally occurring phenomenon. We have isotopes of most of the elements that naturally occur. Now, that's not to say all of them naturally occur, but we do have, most elements do have isotopes. Okay, and isotopes are going to be identical in most of their properties. They will have slightly different masses, but their behaviors with respect to reactivity will be very similar. The only difference usually is with respect to radioactivity. So if you look at the example that we have here, I want you guys to look at the center of the atoms here. Okay, notice we have different superscripts here. Remember, this superscript represents the mass number. Okay, so remember, mass number is protons plus neutrons. Okay, so we have one proton here. Why? Because obviously we need protons to identify the element. Hydrogen only has one proton. So in this particular isotope of hydrogen, there is only a single proton in the nucleus and no neutrons. In this example, notice that there is a superscript of 2. Okay, there's still only going to be one proton because that identifies the element as hydrogen, but there is also the presence of a neutron in the nucleus. So mass number here is 2. Mass number here, 3. Okay, still only one proton, but now 2 neutrons. Okay, so the mass number up above is going to be represented by 3. Okay, so these isotopes are all different from each other with respect to their masses and somewhat towards their reactivity behavior. However, notice they all have the same number of protons that identify them as a hydrogen isotope. So let's go ahead and talk about the hyphen notation for isotopes in elements. Okay, so if we go ahead and we look at these examples, notice we have beryllium-9, magnesium-26, calcium-41. Okay, so the 9, the 26, and the 41 are the mass numbers respectively. So this is how we write out and identify the specific isotope we're discussing. So the mass number is what we have written here after the hyphen. So mass number, okay, and this is how we indicate the isotope that we are discussing. Now guys, I once again want to point out that the mass number is not available on the periodic table. Now some of you guys might be looking here and say, oh, this is basically the same number. The answer to that is that this number is the average atomic mass, which is a weighted average of all the naturally occurring isotopes that occur for that particular element. So actually this is a calculated value, and we're going to actually learn how to do that next lecture. But I need you guys to put in your head that the mass number is not available on the periodic table, and that this is how you would express it when you're talking about beryllium-9, magnesium-26, or calcium-41 isotopes. Okay, so what I want you guys to do really quickly is I want you to pause this slide, and on a separate piece of paper, I want you to answer each of these questions. When you return, we will discuss each of the answers, and you can check yourself. Okay, so what is the mass number of an atom with 15 protons, 15 electrons, and 16 neutrons? Okay, so we know, guys, that mass number is equal to the sum of the number of protons and the number of neutrons. Okay, so if we have 15 protons and 16 neutrons, that is going to give us a total of 31 as our mass number. Okay, so the next question is, what is the element above? Okay, so the identity of an element is based on the number of protons. Okay, and the number of protons can be determined by looking above the element symbols on the periodic table and finding the atomic numbers. Okay, so if we go ahead and we look at a periodic table and we look above the element symbol, we're going to go ahead and look for the element that has a 15 above it. Okay, so if you go ahead and you scan over, you will find phosphorus, which is represented by the letter P on the periodic table. So phosphorus. Okay, and specifically, since we know our hyphen notation, we can also say it's going to be phosphorus, specifically 31, because we know how to do the hyphen notation. Okay, so for the next question, how many neutrons are in this isotope here? Okay, again, we're going to take our knowledge of what this number represents, which is the mass number. Okay, and that's your protons plus neutrons. Okay, and then also utilize our periodic table to find chlorine. Okay, so if we go ahead and we look at our periodic table, chlorine is represented as Cl. Okay, and if we look above the element symbol, we know that it has 17 protons. Okay, so it has 17 protons, so that means that the difference between our mass number and the 17 protons will give us the remaining neutrons. Okay, so 37, which is our mass number, okay, minus our 17, which is our atomic number, okay, which represents our number of protons, is going to give us a total of 20 neutrons. Okay, and so that's how many neutrons are in the nucleus of a chlorine 37 isotope. Okay, and so the last question down here states that neutral atoms of carbon 12 and carbon 14 both have the same number of what subatomic particles. Okay, so remember, the identity of an element, so in this case we're talking about carbon, is always dictated by the number of protons. So if we go ahead and go to our periodic table, we find carbon, which is represented by the letter C. We look above it to get our atomic number. So the atomic number for carbon is 6. So carbon has 6 protons. So both carbon 12 and carbon 14 have the same number of protons. Okay, but also because we're talking about a neutral atom, as discussed earlier, in order for an atom to be neutral, the positive and negative charges have to balance out. So since I have 6 protons in both these isotopes, I also have to have 6 electrons. Okay, so the number of protons and the number of electrons are both the same in both carbon 14 and carbon 12. The difference between each of these, of course, is the number of neutrons.